All right, let's start. Dearly Father, we thank you for this morning. Thank you for the students. Thank you the hurricane hasn't hit us directly yet. I pray that we'd be able to get through this class without classes being canceled and learn some new material. Lord, in your name I pray. Amen. All right, so upon Sharon's request, I'm going to give the hint about the homework, how to show that the polynomial of nth order is bounded as a separate add-on, which I was going to record the other day, but then I got engaged in some conversation about Trump, which wasn't really that interesting, but nevertheless it happened, and so the video is not already posted. The Trump. I mean,
Were you talking about his hair?
How you are going to vote for him?
how am I going to vote for him? I mean, will I have a choice to not vote for him is really the question.
You always have a choice.
You always have a choice. That's funny. I mean, I wasn't old enough to vote for Reagan, so I never really voted for anybody I wanted to vote for. You know? One of my colleagues says he never votes for anyone, he always votes against the other person. Sad but true. Okay, so I want to tell you about some. So the theme, if you haven't picked up on it yet, and I admit sometimes I was like, in my preparation for this lecture, I was like, why are we doing this? What is this? And then it finally hit me. Duh. We are showing applications. We were showing what it means for, a function and its component functions u and v to be harmonic, or u plus iv to be holomorphic. What does that mean? What are some applications of it? What are some implications of that, right? And we've seen different properties. We know, the level curves of u and v give you orthogonal trajectories where the complex derivative is not zero. That's interesting, right? You have this conformality. If you have w equal to f of z, it maintains the angles between curves in the domain and the image. They're harmonic. I mean, solutions to Laplace's equation. There's just so many different aspects of what it means for a function to be complex differentiable, right? So this is continuing that discussion. In particular, we're going to talk about the application to fluid dynamics and perhaps electrostatics. And if I play my cards right, I'll show you a little bit about conformal mapping today. Okay, so when you're thinking about vector fields in the plane, that's the central thing we're kind of working with today, vector fields in the plane. And in particular, there are two kinds of integration that you're interested in. If you have the vector field v equal to, say, p comma q, right? So this is a vector field in R2, which of course we can identify with C. Then there are two kinds of integrals you can do for this vector field in the plane. You can talk about, for a curve gamma, you can talk about so you can take the vector field and you can dot it with the unit tangent to gamma, right? Integrate along arc length, right? This gives you what's known as the circulation of V along gamma. Or it's also, if you think of V as being a force, this gives you the work done by the vector field V around the curve, right? This we study in some detail in Calculus 3. This should be familiar to you, especially when I rewrite this in its usual differential form, right? So this is the so-called circulation or the work of the vector field. But there's something that's a little bit less known, but it's also interesting, which is the flux of V through gamma. So circulation along gamma, flux of V through gamma. And so the flux is the integral of gamma V dot the outward normal ds. So let me just draw a little picture. Here's gamma, oriented in the usual counterclockwise way, all right? We assume that gamma is counterclockwise oriented here, as to not be weird. The tangent, well, that's easy. Everybody knows that. Unit tangent just looks like this, right? And if xy is the, if a point on this is x comma y, then surely the unit, and if it's arc length parameterized, right, then surely the unit tangent's just dx ds, dy ds. You guys agree?
Yeah.
Good. So for example, this t, what happens, you get v dot dx ds comma dy ds, and so the ds's essentially cancel and give you this in some heuristic sense. See that? If you plug this up into here, you get that by just canceling the ds's. Now, where's the unit normal? Where's this n? It's not the Frenet normal. The Frenet normal points towards the center of curvature, which would be inside. The outward normal is this guy. All right? So there's your n. And how is n related in terms of, if we assume that the curve is arc length parameterized as to not be annoying? Can you tell me what the formula is for it? How is the red arrow related to the blue arrow?
It's perpendicular to it. It's a negative reciprocal.
Negative reciprocal, you got two choices. So I'll choose one. Minus dy ds, comma dx ds. I'm 50-50, I'm right? Does that work? Now you can just check different locations and see that it makes sense, right? So, for example, if you're going up, so you'd have dy ds positive, the normal is going over, like that. Uh-oh. Looks like that's not the right choice, because if I put a minus here, that would make this point that way. See that? Look at this arrow. That would be 0, 1. That would make this minus 1, 0. So this is not the right sign choice, right? The sign choice we should make is this one, right? Okay, so with that, you go up in here. So you have integral along gamma of PQ. Well, integral over the, whatever the arc length domain is, I, let's say, PQ dot dy ds, comma, minus dx ds, right? And what does that leave you with in terms of a differential form integral? In other words, the dx dy notation. See what you get? You get, I believe you get p dy minus q dx, right? Oh no, that is not what I have in my notes. That is not cool. Did I talk myself out of the right sign? Think about this more carefully. So T
N is the red arrow, right?
Yep. I think that's right.
Could your notes be wrong?
I guess so. Unfortunately, I don't have a copy of Gamelin right on me. Well, let's just try it out. So what would we expect to have positive flux? Can you think of an example? How about this? V equals to, how about x plus iy, right? So this is basically the vector field, x comma y. It's the radially, it points out radially, right? So if I calculate the flux of this vector field through the circle, I should get something, right? geometrically, if you look at the unit circle, gamma, right, then this vector field is always like this as it crosses the unit circle. So what the flux is calculating, right, is it says you take a little ds like this, right, and then you calculate the normal component to the vector field, and ds dot that normal times the normal component gives you the little bit of flux to that little bit of ds, and then you add them up all the way around, you get the net flux through the curve geometrically. Okay, so let's see here. This has x equals to cosine theta, y is equal to sine theta, 0 less than or equal to theta less than or equal to 2 pi for the unit circle. And so if we calculate the flux of this thing, so we're trying it out. I feel like, I don't know, I'm annoyed. Okay, so then what happens? What's my p? P is x, right? So I have x dy. Oh, sorry, I put the 2 pi. X is what? X is cosine theta. Dy was what? Cosine theta d theta. And then minus q. Q is y. So minus sine theta times minus sine theta d theta. All right, so we get 2 pi. So I think what we derived today is correct, and my scribbled handwritten notes are. It's not even looking at the notes at the moment. I'm looking at what I scribbled down this morning. Let me check your notes. Of course, there's no other errors in my notes, so it would be really shocking if there was an error here. Right, Nathan?
Right.
Yeah, okay, thank you for supporting me in this contention. Very good. Let's see, I have the flux is q dx minus p dy. So I somehow have minus what I should have at the start of section 3.6 of my notes. All right, okay. So fine. Anyway, what's on the board is correct. So the notes are off by sign. You with me so far? All right. So I need a marker. So do you guys remember Green's theorem? The different versions of Green's theorem in the plane? Do you guys know about that? Did you see flux in Calc 3 for plane in the plane, or just in the surface?
In the plane.
In the plane? Okay, good. It doesn't.
Going to do some material.
Ah.
This is the second time this week that you've been happy with how far you got.
Good. I am happy.
We must have had more snow days. I think we skipped it.
Yeah. How long ago did you do it?
You did it semester after me.
Yeah.
Okay, so let me see here. Let's try to make some connections here. So let me well, rather than just going math, let me go ahead and make some physical assumptions here. So we're going to talk about fluid flow. And so the basic idea is this. We're thinking about the flow of fluid in some sort of like two-dimensional sense, right? So there's nothing too interesting about the depth of the liquid. It pretty much behaves uniformly from top to bottom. So you can think of it as two-dimensional. And there's some other assumptions. All right, so these are the assumptions we make. The V I've been talking about is the velocity field. All right, so number one, V of Z, or I'll just say V is equal to P plus IQ. Right, that corresponds to the velocity field P comma Q. The velocity field of the liquid. All right, point number one. And we're assuming that we're looking at a time-independent case. So it's whatever the flow is, it doesn't depend on time. All right. So I mean, it's flowing, but there's no difference in the pattern of the flow over time. All right. If you've had physics 2, it would be kind of like we talk about steady currents that go on and on for a long time. It's kind of like that, right? There's motion, but the motion is boring. Yeah.
Now, why are we describing these things in terms of complex numbers? Why does real not suffice?
Well, anything complex you can always reduce to a problem in reals. So, I mean.
But what advantage does this give it? Because you're talking about application.
Oh, well, we'll see the advantage as we go on.
Okay.
So, no sources or sinks in D. And so we're going to talk about fluid flow and I'll just get it out there, simply connected domain. All right, so we're looking at some simply connected domain D, or if you like, star-shaped, all right? So no sources or sinks. In other words, the fluid's neither created nor destroyed inside D, all right? It's like that. The flow is incompressible. What does that mean? That means it has the same mass per area throughout D, the same density everywhere. All right, and 4, the flow is irrotational. What that means, I would say intuitively speaking, is that it's got no really localized, no turbulence. More precisely, you can capture the notion of irrotational is like here's the fluid, right? And if I pick some point in the fluid, right? And if I look at a little circle around the point, then the circulation around that point is 0. If you had non-zero circulation around little circles about given points in the fluid, that would correspond to having like twirls, right? Turbulence. So we're assuming non-turbulent flow. So these assumptions basically boil down to smooth laminar flow, which maybe was the language you saw used in physics, for example. Okay, so now let's make the connection with what we learned before. We have this P comma Q, right? We can talk about its circulation. We can talk about its flux, right? What do these assumptions mean about the circulation and about the flux of this vector field? What does no sources or sinks mean? This means that the flux is 0 for loops within D, right? That's what that means. If I was to pick some point, right, and if I was to look at a little circle around there, and if the net vector field's flowing, if there was a flux out of that, that would mean that fluid was if the flux was positive, it would mean that there's fluid flowing from some point inside there, right? That would be a source. And if the net flux was negative, that would be like a drain. There would be fluid flowing out. So we're assuming neither of those happen, right? So that means that the flux is 0 for loops within D. Flow is irrotational means that this actually means that the circulation is 0 for loops. All right? But we can convert those to mathematical statements, right? How so? Flux is 0 for loops within D. What's that say about, what integral does that give us information about? The flux integral, right? That tells us that the integral along a little loop, let gamma be some little loop inside D, all right? So that says that the integral of p dy minus q dx, indeed, and that's true for all little loops in D. I mean, they don't have to be little. I'm just thinking of them conceptually as being little. Logically speaking, they can be big enough to fit inside D. If D is simply connected, you can always deform it to a little loop and get the same integral. Oh, well, I don't know. Can we deform it? Is this form closed? I don't know. How about this other one? What's this one say? This says that the integral along gamma of p dx plus q dy is equal to 0. Again, for all little loops in D. So what does this say? Can you tell me what this says about forms, particular differential forms? Yeah? We have the condition that they're 0 around loops. What is that?
They're exact.
They're path independent, they're exact. But exact implies closed, right? So yeah. So that tells me that p dy minus q dx is exact. And it also tells me that p dx plus q dy is exact. Both of these conditions have to be true at once for the given V to actually be the flow meeting these four conditions. Last year, I made the mistake of thinking, oh, you can just make up an example, and any example you make up will be a flow. That ain't true, because you have to meet both of these conditions at once. So the set of velocity fields which are flows given these four conditions, you can't just make up anything. I mean, there are lots of ones that won't be flows. So then what? What's that say? Okay, so it turns out then we mostly pick on this one. So this is equal to d phi, where now you notice that p and q are real, so this phi is also real. So and it's called the potential. This is the so-called potential for the velocity field. All right. Now, what do you have here? The next step in the argument is to argue that phi has to be harmonic. How can we argue that phi is harmonic? Do you guys have any idea?
Could you just define E in terms of U and B and then just do the derivatives? Show that UXX plus UYY equals 0, or?
Yeah, I think maybe that's the right idea, Michael, actually. I mean, sorry, I'm distracted by my need for finding a marker. So yeah, I think what you're telling me basically is, okay, so P, oh, come on. What is this? Conspiracy. That one works. Okay, it's a conspiracy of me against me, but, oh, come on. Well, those markers are really hard to erase. So this, you can read from this that phi x is equal to P, right? And phi y is equal to Q. This up here, if this is exact, what does this say about the relation of, somehow we need to use both 2 and 4. I used 4 to get the existence of the potential. I somehow need to use 2 to show that it's harmonic. Ideas?
Two to show that it's harmonic, so no sources are synced.
The fact that this is 0 is somehow key. Yeah.
Two integrals of each
Huh.
That's true, but I don't know if it works.
That's interesting. I don't know what that would.
Then you get the integral of gamma dt is equal to the integral of gamma p dy.
I mean, almost certainly doing that will give us what we need, but it's weird.
Why is it weird?
Weird as in wrong or weird as
It's less weird than a lot of other proofs.
Well. What do we want to show? We want to show that phi xx plus phi yy is equal to 0, right?
We could just do proof by picture.
So this is exact. What does that say about p and q from up here? I mean, if this is exact, that means that partial y of q minus partial y of q is equal to partial x of p, right? Because exact implies closed on a simply connected domain. Or wait a minute, always. The other way around is hard. Closed implies exact only on simply connected, right? So that's the closed condition for this one, because it's got a minus in the, see this is the p, and this is the q in our usual notation, right? So what is that? If you take this right here, let me call it star, and then just apply star down here, what's it say about? So if I take, let's see here, phi xx, what do I get? Is px, right? Or partial xp in our other notation, which is what? Minus partial yq, right? Which, by the way, is what? Partial y, phi y, aka minus phi yy. Therefore, phi xx plus phi yy equals to 0. Now, I have no doubt, Nathan, if we did what you said, it would work. I don't want to keep you guys over time.
Yeah, I was wondering if we could use that to show that p plus qi would be complex, so then p and q would be harmonic.
Oh, you're thinking you can show that p plus I, wait a minute, you're thinking you can show p plus iq is holomorphic.
Yeah.
I think we're about to say that.
Yeah, I think you could do that first, though. If you set the integrals equal to each other.
You're saying, so if I, or just I add the integrals perhaps, or?
Yeah.
So adding these integrals gives me, I want to add like an imaginary,
Like you could show that the two, like for the first one, you could make dp1 equal to py minus qdx.
now I'm forgetting here, what was the result we had for, how would we get that p plus iq was harmonic from an integral? I mean, holomorphic.
Oh, do you need p and q to be harmonic?
Well, they will be if it's holomorphic. I mean, but I'm not. Is that a theorem we had? Is that No, not. I don't think we have that yet, or anything quite like that yet. That's chapter 4 kind of stuff. Okay, so anyway, so long story short, we do have that phi is harmonic, right? And then what does that say? Since we're in a simply connected domain, if phi is harmonic, what does that mean? That means that there exists. So phi harmonic on simply connected D implies that there exists some other function, psi, or pitchfork, if you like, on D. Again, real valued, such that what? F, all right, F equals to phi plus I psi is an element of the holomorphic functions on D. This is sometimes called the complex potential for the flow. It has the real potential as the real component, and then this other function, psi, is called the stream function. So psi is called the stream function. Stream function. Let's see here. So this one, if I was to be so foolish as to try to apply what we've just derived for this, it wouldn't go well for me. All right. So there's something I'm leaving out of the discussion so far today, is that the circulation and the flux are also given to you in terms of Green's theorem. Well, the circulation you can look at, it's really the double integral. It's the integral, how to say this? I'm rusty here. Stokes' theorem says what? The curl, right? Oh, I'm sorry, guys. I can't find the words at the moment. I know that this basically boils down to the double integral of the divergence of V over the area. That's just one more step. If you apply Green's theorem to this, you get the double integral, right, over whatever region has gamma as a boundary. And so what is Green's theorem here? It's partial p partial x plus partial q partial y dA. That's the divergence, the two-dimensional divergence. So that's very nice, right? I mean, the flux is the integral of the divergence. Divergence is the flux per unit area. So I know immediately that this doesn't satisfy. This has divergence everywhere. What's the divergence of V?
What's divergence?
Right here. Two-dimensional divergence. So for x comma y, the divergence is 2. In other words, this doesn't fit the four conditions, all right? This example, not an example of a flow which meets our four conditions. So what's an example of a flow which does meet our conditions? I think I have two good examples in my notes. The one is just the constant flow. So just let it be, say, C. So I can, and you can say on, I don't know, whatever you like. Let's say the upper half plane. So the picture would be something like, here's the real axis, right? And I'm going to assume C is positive. So what you can picture the velocity, right? It's just doo-doo, 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 you know? And it's fairly easy to convince yourself, even just geometrically, sorry, Michael, that it has no divergence, because clearly the divergence, by the way of a constant vector field, 0. Right, so if you take the integral of flux around any little loop in the upper half plane, you get 0. And also, it's not going to have any rotation either. It's irrotational. Because if you took a little circle, whatever goes in lines up with one side of the circle, goes the opposite way on the other side of the circle, right? So what's the potential and what's the stream function here, and how does that all work? So we have V equals to C, right? So what are we supposed to have? What's the relation between phi? This means P and Q are what? in our language, P is equal to C, and Q is equal to 0. So we're asking, we've got C dx is equal to d phi. What's my phi? Cx, great. Plus the constant, but I'll leave the constant 0. I mean, there's always some ambiguity in the setting to 0. I'm going to choose my constant such that Cx works. And then what's the, how do you figure out the stream function? What's that? Cx plus the stream function is what? We want psi, the harmonic conjugate, right? So you guys know how to find harmonic conjugates, right? I think it's Cy.
Yeah, that makes sense.
So, I mean, geometrically, that should be obvious already, right? What are the level curves of the potential? Cx equal to a constant, right? So if I set Cx equals to k, I get vertical lines. Right? I mean, this is precisely x equals to whatever that constant is over c. All right? That's exactly the equation. So the orthogonal trajectories to that, of course, are horizontal lines, right? So that means that my stream function is Cy. And so if I set Cy equals to a constant, in other words, y is equal to the constant divided by c. Those are my level curves for that. Those are perpendicular, right? Which means that, yeah, those are the harmonic conjugates. Because harmonic conjugates are orthogonal trajectories. If you can set up orthogonal trajectories and simply connect a domain, it works both ways. If you have orthogonal trajectories for a given harmonic function, then the orthogonal trajectories will also be harmonic. And they come together, the complex u plus iv will be holomorphic. We have that result.
They make in numbers of tic-tac-toe boards, right?
Something like that, but they're curvy, generally speaking.
Okay.
And so our f of z, our complex potential, is c times x plus iy. And obviously that's CZ, right? So clearly CZ is holomorphic. In my saying that it's on the half plane is pretty much artificial. You can easily put this flow on the whole plane, right? You see it? Now, do you see why we call it the stream function? The level curves of the stream function are streamlines. If I was to put a little drop of dye in the liquid, that dye would make a line along the stream function's level curve. On the other hand, the potential function, the velocity field is going perpendicular to that. Make sense? Well, I hope so. See here, I think I have another slightly more interesting example. In this example, what? Sharon has a question. Okay.
I don't know if that's it, but when we're talking about this, like, it's literally like fluid, like liquid, like all of the running.
Yeah, like just a liquid running along the ground. So essentially, the height of the liquid doesn't really come into play.
Get rid of these assumptions and do similar types of things and make it more interesting. So the assumptions are very low.
Well, there's interesting stuff. All the interesting things happen on the boundary.
I'm not really interested.
Ah, ha, ha, ha.
Can the liquid be cake batter?
I don't know. It probably depends on how much liquid you've added to the cake batter, I suppose.
Maybe
I just
coffee
keep thinking,
from nothing
it's like sewage waste, and I really
I'm hopeful my mic did not pick that up. Let's see here.
you can edit it out.
Here's an example that is slightly violating our hypothesis, but it's somewhat illustrative. Suppose you have the velocity field x plus iy over x squared plus y squared. So basically I want to see, can I find a potential for that, And, well, yeah, I can. It turns out if you use phi of x plus iy equal to the natural log of the square root of x squared plus y squared, that'll do it.
That's your potential function? Is that what you said?
Yes. Now, I've been vague about the domain, right? So I suppose you might recognize that this is the natural log of the modulus of z, right? So what's the stream function then? Yes. So we can recognize f of z is natural log of the modulus of z plus I arg z. Hey, what's that? Well, that's log of z. So this problem is a little bit more interesting in that, well, it violates one of my assumptions at least. I mean, it depends on the domain. If you look at the slit complex plane, I think we're fine. But if you try to do this on the punctured plane, well, let me show you what's going on. I mean, we can understand it even though we violated one of the assumptions. So the velocity field is outward pointing, right? It's like, here's the picture of V, right? If you set phi equals to a constant, what do you have? You get the modulus of z is equal to e to the c. In other words, here's the level curves of the potential. They're circles. What are the streamlines? You set arg z equal to a constant, right? That's just saying that the angle's constant on the streamline. So the streamlines are like that. Though there is a divergence to this field, right? Where's the divergence coming from? The fluid's diverging from the origin. The origin here is a source. Now, I've talked about fluid flow, right? But you can just as well talk about electrostatics. Who here cares about electrostatics? Lauren cares. Aren't some of you electrical engineers? No? Oh, there's no electrical engineers here. Oh, why are they taking? They should take this class. Man. So what kind of are there no engineers here? Why am I doing this section? What on earth? Oh man. We could have just done math. Look at this. I've cluttered the course with this fluid flow nonsense. Man. No one even likes engineers. Oh, Sharon.
They just file on that.
Sharon. Well, if you'll forgive me this further comment about physics, I'm going to make it because at least Lauren cares. So the electric field, right? If the electric field is PQ, then the potential function here, I would usually say the electric field is minus the gradient of the the potential. Unfortunately, I usually use V for the potential, or I use phi for the potential, both of which are bad here. So if you'll let me, I'm going to use, I don't even know what letter to use for the electric potential. 7, oh my gosh. Not today.
Do a happy face.
Happy face.
Do a ringing cloud.
Oh, you guys are no help. I'll do alpha. So alpha is actually like the voltage function. Since I've already used up. What's that? So, if you look at this, then you guys made me figure out what I was going to say. Good job, people. This no sources or sinks becomes no charge inside the domain. Let's see here, irrotation. Well, I mean, it is what it is. So that says that if you take the integral around little loops, it's a conservative vector field, basically. Anyway, you can also do basically the same song and dance for an electric field. If I do this example I had over here, if I think of V as being, instead of, think of this as being the electric field, if you will, right? Then this would correspond to something like a point charge at the origin, right? There'd be like a point charge at the origin. The electric field the field lines are the streamlines. But the difference is, of course, if this is minus, this would be minus d alpha is the difference. So as you flow out, you're going to lower, I think, lower and lower potentials. If you follow the field lines, you go to lower voltages as opposed to, without that minus, you go to higher potential levels. It's also in Gamelin. He doesn't have the minus for the potential. Mathematicians don't like to put a minus there because it adds some unnaturalness to things we say, but it's necessary if it's going to be representing potential energy per unit charge. So what can I say? All right, so that I think is enough that you at least have seen what fluid flow is, and we can go on about our life. I did want to show you, I think, is a more interesting thing mathematically, and that's just the raw question of solving the Laplace equation. And so we still have a couple minutes. I'll show you. So here's the basic thing: is Laplace's equation is what? It's uxx plus uyy equals to 0. How do you solve that? Well, the amazing thing is if you can just write down a holomorphic function, its component functions are harmonic, right? So think about this. If I want to solve Laplace's equation on the upper half plane, and I have boundary conditions that I have to fix, so I'm going to add some boundary conditions. I'm going to say that, u has to be, u of z has to be equal to 1 here. U of z has to be equal to minus 1 over here for x greater than 0, for x less than 0 and y equals to 0. Okay, in other words, for the positive and negative real axes. And I want to solve. This is also the Laplacian squared of u. I want to solve the Laplacian squared of u equals to 0 on this upper half plane. How can I do that? And I want these boundary conditions. So what I'm telling you is you have almost what you need if you just look at the argument. What's arg of z? It's harmonic, right? Because it's the imaginary component of the log, right? Remember? Log z. So the fact that I know that the logarithm, the right branch of the logarithm at least is it's harmonic up there. So I know arg z is harmonic. And how does it work though? So it's, on the real line, it either goes to what? It goes to 0, or it goes to, what does it go to on the negative? Is it pi or is it minus pi? I forget.
I think it's pi.
Pi, right. Now we're short on time, so you'll forgive me if I'm lazy and redefine the problem to suit our purposes. A 0. Now, I'll leave it 1. I won't be lazy. I'll leave it as 1. All right, so what do you want? What's your solution? U is equal to, check it out, folks, 1 over pi arg z. That is a solution to Laplace's equation on the upper half plane. That satisfies those boundary conditions. You're like, well, who cares? Well, what if I wanted a solution on a disk, right? Such that maybe, I don't know, maybe half the disk has boundary condition 1 and the other has boundary condition 0. And I want to solve del squared u equal to 0 on that. Well, if I can find a complex mapping from here to here, which maps the boundary in the right way, it turns out that you can transport this solution, which is easy to find, to this over here, which is not so easy to find. And so doing, you can solve rather complicated boundary value problems by transporting from the standard half plane to the disk or something like that. So I think I'm going to spend another. I'll spend another class just on this problem. Show you some techniques for it. I have a great I have this Fundamentals of Complex Analysis by Saff and Snyder. He has a section where he goes over basic constructions from either half planes or washers, and shows you some basic fundamental solutions you can solve Laplace's equation for these. And then you guys kind of already know the fractional linear transformations. Those are what you need to take those standard solutions and transport them over to more complicated shapes. So that's what we'll look at next time, which puts me a little bit behind, but since I started talking about this, I want to at least get to the interesting math of it. So I'm going to stop here for now. Thanks, guys. I thought we were going to get rained out today.
There's still